Hello, everybody. It is really a great pleasure to be here with all of you. I cannot see your face, but hopefully you can see mine. And welcome to this second week of this school on particle physics, celebrated jointly together by ICTP in Trieste and ICTP in Sao Paulo. In this second week, you see there is a variety of lectures, but I'm the one taking care of this topic as phrased by the organizers, gravity wave probes from stochastic sources. So let me zoom in into the topic and then maybe make the first observation, which maybe the very attentive and observant people may have made already by themselves, which is if you think of what I was writing in the first transparency of my presentation, instead of writing stochastic sources, I was writing rather talking about cosmological backgrounds. So let me make the first profound and deep comment before we really start, which is cosmological backgrounds are by construction and by default always stochastic backgrounds. So actually, whenever we talk about the stochastic backgrounds, they mean this means necessarily backgrounds of cosmological origin and vice versa. Okay. Now we can make even a second, also very deep and profound comment, which is the acronym GW. It's going to stand for gravitational waves. So please bear it in mind because we are going to use it all the time. So let's say that before we start, there is a motto that you should really have in your mind, which is that whenever we speak about gravitational wave or gravitational wave backgrounds of cosmological origin, this means we are talking about the stochastic backgrounds and vice versa. Okay. So having made this clarification, let me then move on really with the beginning of the lecture, my first lecture on this topic, cosmological backgrounds of gravitational waves. And since this is the very first lecture, every time I want to start a lecture or talk about something which is a whole set of ideas, I think it's very interesting to give, first of all, a motivation. Of course, my motivation is biased because I'm a particle cosmologist. So I'm going to give you my own motivation, but I think it's still good enough to get into the field. So in order to get the motivation spelled out, let us start by celebrating something, realizing how important it is. We have detected by direct detection gravitational waves for the first time really very, very few years ago. And you should really appreciate that this is a milestone in physics, both in astronomy and in theoretical physics. And it's only taken us a century, literally 100 years. So you should really appreciate and take a moment, okay, breathe in, breathe out, and really consider how relevant it is these times we are living in. We've learned a lot of things from the observations made so far. To begin with, we know now for certain that there are order 10 solar mass black holes, okay, that they exist. Secondly, it's clear from the kind of observations we are making that we can test the paradigm of black holes and neutron star physics. We can test furthermore the paradigm itself. Do you guys see the mouse pointer? Can any of the organizers confirm?
Yes, yes.
Okay, excellent. So we can test further the underlying theory of gravity. So far, there is no deviation whatsoever of general relativity. And also we can observe the universe through gravitational waves in general, okay? So now the first points I was emphasizing here are very, very interesting, yet this is not what I'm going to be focusing on myself in these lectures. Don't get me wrong, they are very interesting and certainly stay tuned because there is lots of fun coming from these topics. And certainly pay attention to the lectures by Masha and by Francesco because I'm hoping Masha will cover the idea of using these astrophysical sources to probe fundamental physics, and hopefully Francesco will introduce primordial black holes as dark matter. Okay? But what I'm going to focus myself here has to do with the fact that we can observe the whole universe with a new pair of eyes, which are those eyes given by the gravitational waves. Okay? And I emphasize the whole universe because this means I want to do cosmology with gravitational waves. So if we talk about cosmology, this implies that either we're going to do late universe or early universe. Okay? Late universe would be the measurement, for instance, through standard sirens of cosmological distances, or measuring the Hubble rate, equation of a state, cosmological parameters, etc. However, I'm gonna rather focus on the early universe for a simple reason. It is in the early universe where there are high energy particle phenomena that are connected with high energy physics, fundamental physics of the kind I think this school is mostly about. So the school is on particle physics, so obviously makes all the sense that this is the part where we focus on. No? Now, if I want to study with gravitational wave these high energy phenomena from the early universe, what is the question I want to ask myself? Well, the question is the following. Can we really prove high energy physics or some kind of phenomena related to high energy physics using gravitational waves? And if so, how? So answering these very basic questions is precisely at the heart of these lectures. Okay, this is precisely what I'm going to cover. And you should realize that there is an underlying, let me say, assumption or a statement here, which is the fact that gravitational waves, I'm assuming they can be used to probe the early universe. So now I have a first question to all of you, which is why? Why do you think I can think of using gravitational waves as a probe of the early universe? And I don't know if anybody wants to type it there in the chat, but as a tip, let me tell you that there is one and only one reason, actually. So any guesses? By the way, I don't see the chat to the organizer, so if somebody writes something, you should tell me.
Yeah, I let you know. Come on, guys, don't be shy.
Well, since probably some people
So there's an answer.
There's an answer, yeah, which is?
So Roberto Caroli says for models of inflation.
Okay, that would be like very specific answer. So what I was really thinking about is the following. The only reason why we can think of probing the early universe is because of the weakness of gravity. Only because of this aspect, we can think of seeing the early universe through gravitational waves. Why? Because this has a clear advantage. Gravitational waves are so weakly interacting that they decouple immediately upon production. Of course, at the same time, this is the reason why it's so difficult to detect them and it took us so long. Okay? So focusing on the advantage, gravitational waves can probe the early universe because they decouple, which means whatever spectral shape they were produced with will be retained through cosmic history. So for a specific high energy physics phenomena, there might be specific signatures in the gravitational wave backgrounds. Therefore, by measuring them, we could infer information about these high energy phenomena. Okay. Now, what kind of processes or phenomena of the early universe are we talking about? Well, let me introduce you to the early universe. So people, early universe, people. This means early universe, just the very first second of the universe, which is typically divided in 3 periods: inflation, reheating, and thermal era. Okay, this is just a very, very small fraction, 1 second, of the whole cosmic history of the universe, which I understand that mostly was covered by Rogerio in his lectures. He also developed a lot on the very first moments of the universe. But let's say I'm going to focus myself only specifically in this very first second. Okay. So as one of our colleagues was saying in the chat, there is the case of inflation, but there is also reheating and thermal era. So in particular, there is a number of cases of phenomena, for instance, quantum fluctuations in inflation, particle production either during inflation or reheating, phase transitions either during reheating or thermal era, and possible cosmic defects after a phase transition. All of these phenomena, which can be very different from each other, but energetically speaking, they can be very wild, very powerful. So that what they share in common is that all these phenomena actually are capable of radiating gravitational waves. So the aim of my lectures are precisely to describe, on first place, what are the properties of these gravitational wave backgrounds, which remember are the stochastic backgrounds, and in second place, what is our ability as detectors, as persons, to detect them and infer the information from the high energy phenomena that created them in first place. Okay, this is the motivation and the logic that's going to follow in the lectures. So essentially, when we talk about sources of stochastic or cosmological backgrounds of gravitational waves, we can think of 4 categories: the inflationary period, the reheating after the universe following inflation, the possibility of having a strong first order phase transitions, and the possibility of producing cosmic defects after these phase transitions. There is actually a notion of chronology. So there is first inflation, then reheating, then possibly phase transition, possibly cosmic effects. Okay, so that defines the natural order of the outline, the guideline of my series of lectures. It's going to be very simple, the division, because we are going to talk about gravitational waves from inflation, then reheating, then phase transition, then cosmic effects. So a possible way to split the time would be perhaps to make 1 hour lecture of all of them, because in total we have 3 lectures of 1.5, so 4.5 hours. So we could think of doing this and then have half an hour of discussion. However, I think the organizers insisted me a lot on the fact that I should be very pedagogical and we should not give for granted the notion of any basic concept. So therefore, I think it makes sense that we introduce an extra chapter on the definition of gravitational waves, and we shift the numbers so that in reality, what we are going to do is to dedicate our entire whole lecture today to the concept and construction of gravitational waves. Okay. Then, following on the second lecture on Wednesday, we will cover gravitational waves from inflation and from re or preheating. And finally, in the third lecture, we will cover gravitational waves from phase transitions and from cosmic effects. All right. So let's start. Hope you had some good coffee, because you are going to need it. So let me begin by giving you a primer on gravitational waves. First of all, we need to establish what is the gravitational framework. And we're going to be working with general relativity. This is a metric theory that relates the geometry of space-time with the presence of matter in the universe, no? in any part of the universe. It's written in the language of tensors, and we're gonna get to see a lot of expressions of this kind. For instance, this is the space-time invariance under a general space-time metric. Okay, and it's based on a symmetry, the symmetry of a general coordinate transformation, diffeomorphisms. Okay? Now, this would be, how to say, the transparency one, and normally I would jump into the definition of gravitational waves right ahead. But I think it is advisable that maybe we make a small break, and maybe not even so small, and within our primer on gravitational waves, we also introduce a shorter primer on general relativity. There will be some overlap with some of the lectures from Rogerio, particularly his first lecture. But I think it's still good that we define from the beginning certain notions and vocabulary, since whenever I will introduce the gravitational waves later on, we are going to rely on all these concepts. Okay? So let us begin by the principle of all the principles, which is the equivalence principle. As you know, Einstein substituted the action at a distance theory of Newton by the idea of there is a manifold which represents space-time, which has a dynamical curvature. Okay, but let's go a step back and let's start from Newton's point of view. Let us recall something very simple. We know from high school that there is his gravitational law, the inverse square force between two masses. Essentially, it's described by this famous formula, where with the strength of interaction given by Newton constant. No? Okay, very good. Now this law works perfectly fine, even if one of the masses is an extended object, as it could be the Earth, for instance, and then the second mass is us on the surface of Earth. Okay, it works absolutely the same, just comparing the distance from the center of Earth to our location on the surface. Okay, excellent. Now, a trivial observation, yet very profound, and now I'm not joking as before, I really think this is a profound thing that was noted for 2 centuries, and yet it was Einstein, the only person who really made something out of it, is that Newton's law allows you to define what is the surface gravity, or if you want, the gravity at the surface of Earth from its own law, okay? And it's this famous 9.81 meters per square meter. And now we know that if we balance the Newton's gravitational law with his second law of dynamics, in principle, assuming that the 2 masses entering into this game are the same, this means that the acceleration in any location on the surface of Earth, it's the same. Okay, it's dictated in principle by the mass of Earth. Okay, so it's a universal acceleration. And this was known, of course, for 2 centuries ever since Newton, but it was Einstein who really made something out of it. What did he make out of it? Okay, let us think of the following Gedanken experiment that Einstein was so used to do. We put an observer in a kind of elevator. We close the elevator so the observer doesn't know what is in her surroundings. Okay, we know she's placed there on the surface of Earth, so there is gravity pulling her towards the center of Earth. Very good. But now let's remove Earth. We know gravity works exactly the same if we concentrate all the mass of Earth in the center. Okay, and it's going to work literally the same manner. The difference now, we've removed the surface of Earth, so essentially we allow our user, our observer, to be in free falling. And what happens when you are in free falling? Well, what happens is you feel no force. Literally, it's the same as if you were out there in space where there is no gravity or no other forces. And this was the profound understanding of Einstein, precisely, that if you are in free fall in a gravitational field, actually you will feel nothing, no force whatsoever. So these two situations seem to be equivalent. So let's push this furthermore, okay? Let us suppose, again, that we have our observer locked down inside the elevator. She sees nothing around her. So she doesn't know that she's there. She just feels gravity because gravity is pulling her, no? And now let's compare the situation of her twin cousin, you know, who is in a space rocket that is accelerating here in the picture in vertical direction with the same strength of acceleration than the gravity of Earth on its surface, okay, with G. Right, so what Einstein once again understood is that these situations actually appear to be identical because our observer inside the rocket, assuming she doesn't know that she's inside a rocket, will just feel a gravitational pull or an acceleration pull, if you want, towards the bottom of her floor. Exactly the same as this other observer on the surface of Earth. Okay? So the situations, again, seem to be equivalent. Now let's elaborate a bit more on this concept. Imagine our observer has some ball and decides to drop it without throwing it, just suddenly it releases the ball and the ball is gonna fall under the gravitational field attraction, okay? Very good. Now, what is the equivalent of this experiment in the space rocket? Her cousin, the one of the observer at Earth, has a ball as well, and she drops it, again, without throwing it in any direction. She just lets it go, okay? So what happens? Because the rocket is accelerating, it will be moving towards, in this case, up position, and there will be the notion that the ball is moving, accelerating down to her floor, precisely for the same reason, precisely in the same, mimicking the same motion that our other observer here on the surface of Earth was experiencing. But in reality, if you look at this horizontal line, the ball never moved. It is all the local effect that the observer inside the rocket feels as she accelerates. As she accelerates, the ball goes away from her simply because she's moving on accelerated motion and she dropped the ball, didn't hold it with her, okay? So once again, it looks like, you know, these situations are equivalent and our observers in reality would not be able to distinguish whether they are locked down inside an elevator on the surface of Earth, or rather they are locked down inside a cabin inside a rocket. Okay? There is no way to distinguish this situation, the one from each other. The local motion of objects seem to be the same. Okay, up to here, possibly it's rather easy to follow, no? But the great insight of Einstein made him to go a step forward. So in order to do this, let us now think of the maybe more intricate, but still, I hope, relatively easy, Gedanken experiment. Let's follow it. So let us suppose that we are in the rocket now, and we are aware that we are ourselves on the rocket, and we have some kind of device that shoots a laser beam horizontally compared to us, okay, in the transverse direction of our motion. Okay. Normally, of course, the beam because it's made of light. It's gonna go at the speed of light. So normally it's gonna reach from one side to the other relatively fast, no? Very fast, obviously, no? Given the speed of light. But now let us think that the acceleration is quite notorious on the rocket, okay? So as the beam starts traveling, what happens is our observer is also moving forward with the rocket in the up direction. And this gives rise to a non-trivial aspect, because if you think about it, since the beam of laser photons is free, it happens the same circumstance with the ball before. In reality, the beam is never moving height. It is rather the observer here accelerating with the rocket. But if you accelerate strong enough, you have enough time such that as the beam starts going from the left to the right side of the wall, it also starts going down, okay? Or at least that's how the observer feels it. So one step further, okay, our observer has gone slightly farther up with her rocket. And then you see the beam still continue on its way to transverse the room where our observer is locked down. So essentially, what is the observer seeing? The observer is seeing a laser beam that is moving on one horizontal direction, say towards her right, or our right, as we are seeing her in front of us. But it's also observing that the beam is somehow bending towards the ground, okay? So if you want, we can trace down the trajectory, and this is literally if she had a device to measure the trajectory of the laser, let's assume she does, this is what should be seen, okay? It's a laser that has motion on two perpendicular directions. One is the natural motion, another one is a consequence on being in a non-inertial frame, which is the accelerated rocket, the spaceship. Okay, very good. So now recall that we've established, this is what Einstein did with the equivalence principle, conceptually, that this situation is the same as the gravity created on any surface of a planet, say Earth, where there is a gravity field. So if these situations are equivalent, what we are arriving at actually is to the situation that necessarily, if they are equivalent, the gravitational field must be bending light. If we are in a gravitational field, like the one you have, for example, when you are over the surface on Earth. Okay? So you see, this is a non-trivial conclusion, which is, however, just obtained from this very simple analogy with the equivalence with the motion in the space rocket, which is accelerating, say, in the opposite direction where the gravitational pull of the field of Earth is pointing to. All right. Okay, very interesting. So, according to the equivalence principle, the gravitational field, any gravitational field, must be bending light. Now, the problem, why they had not noticed this before, or probably not even thought about it, but even if they had, certainly was certainly very difficult in those moments in history, beginning of 20th century, to prove this. This was very difficult because the intensity of gravity of Earth on its surface is, of course, very weak. So they needed, obviously, to go to some stronger gravitational field, and the only one available in that moment was, of course, the sun. Okay, our star, the center of our solar system, has a much stronger gravitational wave field, and therefore will do a better job. The only problem is, since the star is shining all the time, you better do this in a solar eclipse when the sun, the light from the sun is not making you blind directly. Well, and this is this famous Eddington expedition in 1999 to test the theory of Einstein. The idea was the following. We are the observers here. We are placed on Earth. We know already a catalog of stars, okay? People have measured them before. What are their relative locations? Imagine of several stars placed on the sky. And then whenever there is an eclipse, say the moon covering the sun, so you don't get blind by the light of the sun, then you can look at the relative positions of stars. And essentially what they observed in this experiment, if some of the stars that were known to be in a given position in the sky, now were looking to be in a different position, this apparent position. The reason being simply the deflection of light due to the curvature of a space-time, precisely what Einstein was talking about. Okay. Notice that light does not change the speed, but changes direction. Right. So essentially, Einstein, even before he formulated mathematically his famous theory of general relativity, he was quite capable of deriving already all the consequences that it would have. Let it be light bending, let it be red or blue shifting of light as it goes up or against the gravitational field, let it be gravitational time dilation, etc. So the great insight of Einstein was capable of deriving all of these consequences just based on Gedanken experiments of the kind I'm just showing you. Okay. But of course, it was also clear to Einstein, as I think it is clear to us at this point, that in order to make any progress, to make predictions, or to describe this in a more precise manner, we do need a mathematical formulation, right? Okay, so...
Excuse me, Daniel.
Yes.
Maybe I can pass your question.
Yeah, sure, please, go ahead.
Anupam is asking, can you explain how gravitational waves may be suitable to probe the early universe or the very high energy?
Okay, so how gravitational waves are suitable to probe the early universe, this is the aim of my whole series of lectures, okay? So what I'm trying to give here is a basic and starting from scratch description of what are the mathematical tools we are going to use in order to answer that question, okay? So if you want, Anupan, so this wouldn't be the right moment to answer you that, because the answer is going to be the whole set of lectures. It's just that today we are going to make a deviation in order to first bring up what is the mathematics we need, which is that of general relativity. And then in the second part of the lecture, you'll see that we derive the notion of gravitational waves. And in the last two lectures, okay, or in the next two lectures, we will dedicate 3 hours to see how gravitational waves can be used as a probe of the early universe in full detail. So no worry, it will come. Okay?
Thanks.
Yeah.
Yeah,
Is
please
there
go
any?
ahead. No,
Yeah,
there
okay.
are no more
Go
questions.
ahead. Okay, no problem. Okay, so mathematical formulation of general relativity. I do understand that for whoever has studied this, the general relativity, this is basic. But also take into account that there is a great disparity of audiences here. So I don't want to assume nothing. I want to build it from scratch for every detail I'm going to be telling you about. Okay, and this is why we are taking this detour before we answer of how we can use gravitational waves to probe the early universe, this detour to really set up the mathematical tools, which are those of general relativity. So what are the equations of general relativity? Let us think of, first of all, a little bit on special relativity. Let's think of an observer. She's running with constant velocity. And then somebody asks her, please, can you write down a space-time diagram? And immediately what she writes down is what you learn in the high school, that if you are moving at constant velocity with respect to someone, okay, the amount of space you go, it's proportional to the amount of time for which you are running at constant velocity. Pretty obvious, no? But what about if you are accelerating? Okay, you are going at increasingly faster and faster speeds. Well, then the diagram is also kind of obvious, no? Now, for the same amount of time, our runner is capable of doing more space compared to the constant velocity motion she had before. Okay. Well, yes, these are high school observations, but now let's make an Einstein observation. Let us recall that acceleration, okay, if you are blind and you don't know you are being in an accelerated frame, it's equivalent to the effect of gravity. Now, if when I draw acceleration, this corresponds to a curved trajectory in space-time, okay, literally this means that I should interpret gravity as a curved space-time manifold, okay? This is a non-trivial step or a non-trivial assumption, and it's very characteristic, I think, of Einstein thinking out of the box, okay? He's capable of understanding that the equivalence principle, what is really telling us that, of course, the gravitational field, it's a field that depends on whatever the source, but it has its intrinsic properties in the shape of the curvature, okay, of geometrical properties of a space-time that he now promotes to an entity, okay? And you see, you can already arrive into that just making this very simple analogy with the space-time diagram. Okay, let's recall now, once again, our exercise of the person on the surface of Earth that was feeling the gravitational pull equal to 9.81 meters per square second. Well, what Einstein does now is to tell us, hey, listen, it's not a matter of having a gravitational field created by a mass. It's a matter of having a geometry or a space-time manifold with a certain geometry created by the presence of matter. In this case, the presence of matter is Earth. It creates this curved manifold, and then we see a satellite that is orbiting around. From the Newton point of view, this would be the action at a distance. From the Einstein point of view, this is the motion along the so-called geodesic, the minimization of the path in the geometry of this space-time. Okay? So essentially, the essence of the theory of Einstein is that whenever you have a big concentration of mass or energy, this creates a space-time manifold. And then whenever you have objects with mass or with no mass, actually, but maybe with some energy, they will move in this manifold. Okay? So now let's see if we can formulate the equations of general relativity. Let us think of one guy which is hitting a ball, and somehow he managed to give a constant velocity to this ball. So again, if you ask this guy to draw a space-time diagram, he will draw a straight line as before. But now let us think what another observer will see this particular event if she's running with constant velocity in whatever direction compared to the guy who hit the ball in first place. So what happens is that she will actually draw her own space-time diagram. It will be also a straight line, but it actually will not coincide in the interval in time and in interval of position as gone by the ball. Okay, it will be different. And this is something that was also understood since, advent of mathematization of physics, since Newton, that there was this circumstance that if you are running with different velocity, obviously the amount of space the ball is going to circulate from one location to another is not going to coincide exactly with from another observer. So sorry, I said wrong that from Newton they know this. Sorry, this is not at all the case. Sorry, this became manifestly clear only when special relativity was put forward. It was in special relativity that we make this observation, and actually what happens is that in special relativity we realize, or Einstein realized for all of us, and then we follow afterwards, that it is not a matter of the space interval or the time interval you have to compare. It's actually the space-time interval. So it's the difference between the time interval and the spatial interval that is actually the same between as observed by the two observers. Okay? So now introducing some notation that we will use all the time with tensors. The typical notation in special relativity tells us that the infinitesimal space-time interval is equal to the infinitesimal time interval minus the infinitesimal spatial interval. Okay? This can be written, this invariant space-time interval in special relativity in a more fashion manner using the more modern matrix or tensor notation, which amounts to introduce here a metric, which is the metric for flat space-time, characteristic of special relativity, the famous Minkowski metric, with one entry negative, the other three positive, or vice versa. Okay? Well, what general relativity is doing is promoting to dynamical this guy here, the metric, the geometry of space-time. It's not something static anymore, okay, like it was in special relativity. It becomes a dynamical object itself. So the space-time interval is still invariant in general relativity, but in order to work out the invariance, now you need to compare the metric as seen by one observer and another. Okay. So how do we compare this? Well, if this is invariant, then we express the space-time interval in one coordinate system. We express it in another coordinate system, and from here we can solve immediately just using differential formulation. What is the metric from one space-time coordinates to other space-time coordinates, okay? And it's just connected through this general transformation of coordinates. Okay, so general relativity is nothing else but the generalization of special relativity. essentially, it can be, if you want, considered to be split in two parts, general relativity. First of all, there is the equivalence principle that dictates how bodies or entities or whatever moves along a given space-time background. So if you have a space-time background here represented by the metric G star star, you can compute these so-called Christoffel symbols, which are just quadratic forms in the metric. And essentially, you can figure out what is the acceleration in this, let me call it gravitational field, in this space-time metric, due to the presence of this space-time metric itself. Okay? This connects with the first part we were discussing. Now, secondly, there is the principle of relativity, which was the basis of special relativity, but now this is generalized to general coordinate transformations. So essentially, general relativity, it's a theory that states that under an arbitrary change of coordinates, the physics is going to be the same. And the first consequence of this is to learn how the metric is transformed under general coordinate transformation. Second consequence, which is much more elaborated to deduce, so I'm just going to put the answer, is what are the gravitational field equations that describe the dynamics of the metric according to this principle. And this took Einstein several years to do it. It's really a non-trivial step, but at the end it can be done. It can be understood in several ways that the most general, according to certain criteria, equation describing the geometry of a space-time are the Einstein equations, which consist of this Ricci tensor here minus its trace reverse part, and then the energy momentum tensor. So maybe let's emphasize this again. So general relativity is a generalization of special relativity where there is an arbitrary change of coordinates. Sorry, that whenever there is an arbitrary change of coordinates, then the physics is not going to change. Okay? And this implies that the equations of motion for the dynamics of the metric are the Einstein equations. The Einstein equations are written like this. Here on the left-hand side, we are describing the space-time geometry. And on the right-hand side, we have the presence of matter. And this is described through the so-called energy momentum tensor. And the weight of gravity is actually the inverse of the Planck mass, which is related to nothing else than the Newton's constant, to this expression. Okay? Very good. Now, so essentially, this is going to be our gravitational framework in order to define gravitational waves. It's a dynamical metric space-time theory sourced by the energy momentum tensor, okay, which is some property contained by whatever source of gravity, which are essentially any entity that exists. And in order to do it properly, in order to solve these equations, you have to realize that this Ricci tensor, it's actually a linear combination, it's actually a difficult combination of quadratic terms in the Christoffel symbol, which remember is already quadratic in the metric, and then derivatives of these Christoffel symbols. So essentially, the theory of Einstein of general relativity is a very nonlinear theory, very, very nonlinear, okay? So general relativity is our framework that we are going to start using in the second lecture and exploiting. It can be written down in a very simplistic manner. You can write the Einstein tensor here. Einstein tensor is this previous combination of the Ricci tensor with the Ricci scalar here. And the Einstein tensor is a nonlinear second-order operator over the metric, which is the incognita for us when we want to solve a gravitational problem. And all of this is sourced by the energy momentum tensor, which is a property of whatever type of fields or matter. Could it be let it be non-relativistic matter, radiation, so relativistic species, let it be dark energy, let it be topological defects, let it be whatever you want. Whatever you have in the universe gravitates, you plug it here, you will see what is the answer in the space-time it creates, okay? Because it's nonlinear, it's extremely difficult to solve a theory. So very often we do approximations, okay? Approximations and sometimes work extremely well. One basic example of this approximation is the one we do in cosmology. And since what I'm going to describe is gravitational waves of cosmological origin, let me take a couple of transparencies on this point. So if we want to describe cosmology with the theory of Einstein, essentially we need to answer to provide what is the energy momentum tensor of the whole universe. And if we do so, then we will get what is the metric of the whole universe, okay? And how do we do this? Well, we look at the sky with the Hubble telescope. This is a real picture. And we realized that actually, despite the fact that we see many galaxies, if I take a sufficiently large volume, comparing this region with this region, we may come to the conclusion that the universe is actually homogeneous and isotropic. So that is, it looks the same everywhere and in whatever direction you look at. Of course, this is only true in a statistical sense, obviously, because locally we have different galaxies here and there, and obviously, if we have different galaxies, each galaxy is different from each other. But statistically speaking, maybe the number of galaxies of a given type is very similar to the number of galaxies of another type here, so on and so forth. Okay, so in that sense, the universe is homogeneous and isotropic, and I believe Rogerio introduced you then what is the solution to a space that is homogeneous and isotropic. This is the Fredman-Lemaitre-Robertson-Walker space-time background. And this is going to be the metric, the space-time background, we are going to be using when we will describe the early universe in the lectures next days. Okay, it's very simple metric. It has just one dynamical degree of freedom, the scale factor, and another, if you want, a parameter in the theory, which is the curvature, which can only take 3 values, whether the universe is open, flat, or closed. Then there's some invariance that is not relevant. So this metric gives rise to the idea that the universe is expanding, and this is represented in this cartoon. So essentially, there are going to be a number of events all along the history of the universe, and in this series of lectures, particularly, I insist, in the next 2 days, we will focus on the events that really happen at the very stages, early stages of the universe during its expansion histories. See in anyhow lectures by Rogerio, who I believe cover a lot of the details of this expansion history. Okay? For us, now just before we do a small coffee break, before we continue with the second half of the lecture today, the only relevant thing of this expansion history right now is that when we take a given length at a given time, due to the expansion of the universe, we know it's going to grow linearly with the scale factor. So that distance, say between 2 objects, say 2 galaxies, it's grown a ratio of the scale factor in the later moment compared to the scale factor in the earlier moment. So this ratio defines actually what we call the redshift. We take the scale factor today compared to the scale factor at any earlier moment. This defines naturally the redshift, and it will be a natural language that we'll be using all along cosmic history to talk about the redshift. Okay? With this, I finish the digression on general relativity. So we close the parenthesis of this, and I would say we continue with the primer on gravitational waves. What was my first transparency in this primer on gravitational waves was to establish that our framework for gravity is going to be general relativity. This is what I've been explaining in the last 40 minutes. And now we are going to ask ourselves, just before we do the coffee break, how can we define gravitational waves? Since this is a very complicated operator to second order and nonlinear, the natural attempt to define gravitational waves is actually going to be to do perturbation theory. So we are going to consider as a starting point to take a full metric and expand it with perturbations on top of a background. And that will be our approach to define gravitational waves. Okay? And then we will have to plug in here some part of this energy momentum tensor, which will have to be the source of gravitational waves. We will have to learn what is the specific part of this energy momentum tensor we have to take. So this is the approach we will adopt to define gravitational waves. But I propose to the organizers we make a small break of 2 or 5 minutes, whatever they prefer. And then I'm happy to answer any question if there are some.
Sounds good. Are there questions for Daniel right now?
Hi, Daniel.
Hello.
Hi, I am Anupam. Hello, can you hear me?
Nice to meet you. Yeah,
Yes.
I hear you, Anupam, yes.
I am trying to understand the following. If we want to get information about the early universe, then the energy of the probe should be larger or in same order of the energy of early universe. But gravitational wave, the energy of the gravitational wave is very small.
Yeah.
Then because energy of the gravitational wave is very small, then is it useful to probe the gravitational wave as to get information in early universe?
Yes, yes, it is, because the reason why gravitational waves actually are very small, it's because we will see the solution of this equation once we linearize it is sourced by this guy. And now the fact that the source of gravitational waves is very small is not because the energy of the system that produces gravitational waves is small. It's because it's Planck suppressed. Okay. So you see, I'm going to get a very tiny signal here, once we define properly what is gravitational waves, coming from a gigantic source of energy density, or if you want, gigantic energy momentum tensor, comparable sometimes even to the background itself of the total amount of energy in the universe, but that's going to be suppressed by the Planck scale here. And that's what makes tiny this guy. But if I detect this guy, I will infer information from the source, which characterize the property of energy and pressure and other circumstances of the sources. Okay.
Okay.
So it's so be careful with thinking that because gravitational waves are small, this implies that we are not going to be probing high energy physics. On the contrary, we need very, very energetic high energy processes in order to have any survivable gravitational wave that we may have any chance in the future to detect from the early universe, as we will see along the lectures. Yeah.
Okay.
Cool.
Thanks for the question.
Cool. Then we have a question from Ganesh.
Yeah.
He's asking, is there any upper or lower limit where the GR effect can be detected by experiment?
Oh, there is a number of effects that where GR has been tested, of course. Yeah. There is a dilation of time. For instance, if you put airplanes circulating around Earth, the flow of time of clocks, of atomic clocks inside the airplanes goes differently than the flow of time on the surface of Earth, just because they are at a different height. So the gravitational field is different, and this makes the flow of time to be slightly different. And this is fundamental in order to make work the GPS, for instance. Okay, because the GPS are satellites sending signals from certain height above the surface of Earth, and you need to compensate when they send the signal to synchronize with the observers on Earth the fact that they feel a different gravitational field. Okay, so that's certainly one effect. Another one that has been detected to prove GR, general relativity, is the deviation of light in a strong gravitational field, as it was the Eddington experiment. All right. The detection by LIGO of gravitational waves, that Masha is going to tell you a lot of details about this, LIGO and Virgo network, are actually in very, very good agreement with the prediction of gravitational waves from general relativity. Okay, and this maybe connects more with what I'm guessing is the aim of your question. Can I detect a deviation of general relativity? Well, we could, if, for instance, some of the gravitational waves we've observed with LIGO Virgo didn't have the pattern that we had predicted with general relativity. But what's happening so far is that everything that is being detected there is absolutely in agreement with general relativity. Okay, so far there is no particular observation that tells you there is deviation from general relativity. There is, however, many observational experiments that put constraints into parameters that deform the theory of general relativity. And these are the parameters that characterize so-called modified gravities, and these parameters are compatible with zero nowadays, essentially. Okay, with high precision, I must say, with very high precision.
Okay, thanks. Ganesh says, okay, so I think that you answered this question.
I hope so, but if not, feel free to elaborate on the Slack channel.
Cool. Then, so we have two more questions for the moment. The next one is from Alexander Bonilla Rivera, and he's asking, is the same to say that the space-time is absolute than that the line element is invariant?
No, this is not the same. This is not the same, because absolute means, for instance, the notion in Newton physics, okay, where the flow of time does not depend on the observer, and space doesn't change. The geometry of a space doesn't change with the motion of the observer. Okay, but in general relativity, the flow of time and the actual properties you feel of a space change with your own motion or with your possibility of putting some very large concentration of energy, okay? And it will perceive differently by different observers. However, the line element will be invariant between these different observers, even if they perceive different properties, if you want, geometries of the space-time, okay? So it's absolutely not correlated, the notion of absolute space with the invariance of line element. Yeah.
Nice. So next, we have a question from Felipe, and he's asking, why do we need to assume both isotropy and homogeneity for cosmology? Wouldn't it be sufficient to assume only homogeneity?
Very nice question. Thank you. Let me go back to here. So the reason why we assume both is because, and this is a question I bounce back, Felipe, was it?
Right.
Could you think, Felipe, of a space-time that is homogeneous but not isotropic? So I don't know if you've ever thought about that, but the answer is actually pretty simple. You could think, for instance, of a homogeneous electric field, but as electric field it has a direction. So if it points in a given direction everywhere in the universe, that would be a universe that is homogeneous but not isotropic. However, when we look around ourselves, when we look, around our point of observation to the sky, we see that there seems to be no privileged direction, okay? So from our local point of view, if we think there is no privileged direction and we assume the universe is homogeneous, this means that from every location, there is no privileged direction, and therefore is necessarily isotropic. And this is why we need to assume the two things, okay? And this is, once you assume that, that's the metric you take is Freeman-Lemaitre-Robertson-Walker, which happens to describe very, very well, with outstanding precision, the evolution of the universe according to many observations. Whereas other metrics that people have proposed, where there is maybe a special center of the universe close to our location, or there is a privileged direction, they usually fail in many of the observations. To begin with, the perfect almost isotropic background of a cosmic microwave background with the very tiny anisotropies around this almost perfect background, you know. So if the universe was not isotropic, it wouldn't make any sense that we see it the same in every direction modulo the small fluctuations we detected. Yeah.
Okay. There are two more questions. Do you want to take them now, or?
I think maybe we can postpone for after, because just in case.
Okay. So Miguel, Felipe, keep these questions. If I forget, I'll try to remember for later on.
Can we maybe break 2 minutes, Joan? So
Yeah,
I grab a bite, you know, I disconnect myself 2 minutes and I'll
Sure.
back.
Let's break 2 minutes. We all drink a glass of water or coffee.
Exactly.
Come back.
Thanks.
Okay.
Thanks. See you now. Okay, I'm back myself, so just to let you know.
Cool. I'm thinking maybe you could answer these two questions that were left, because
yeah. No, I have no
very
problem.
much to do with the discussion we had now, so I think it's a good moment.
Okay, sure, go ahead.
So Miguel is asking, if gravity is seen as a curvature of space-time, could it mean that gravity is not a force anymore, or it keep being a force but another interpretation? That's the question.
Okay, well, actually, what your question is reflecting is that you still have the notion of a force described by the typical view that was developed in the 18th and 19th century after Newton, where there is a field which acts at distance. Okay. The modern interpretation, as probably you are familiar with, is that all interactions are described by fields. Okay, so all forces, which in the modern vocabulary we rather talk about interactions, are described by fields. And let it be electromagnetism, let it be weak forces, strong forces, they are all described by fields that are the carriers of this force. So in gravity, there is no difference. There is the field, which is the gravitational field, okay? And in that sense, it's not different than the other forces, simply because we call them interactions in general when they are described by fields, no? Maybe the big difference is that here the field is a space-time itself. So it's the arena where the other interactions take place. So that's the amazing thing of gravity, that it has the same kind of description at the classical level than the other field theories, than the other interactions, but however, it is really describing the arena, the circumstance where the other interactions propagate. And now what makes it very, very different, of course, is the fact that we don't know how to quantize it properly, whereas the other ones are all quantized and in the framework of quantum field theories, the framework underlying particle physics, which is a very successful framework, you know, as the model standard model is a very successful framework to describe high-energy physics. And the next question, yeah?
Yes, so Felipe, I think inspired by your answer to his question about disentropy, now he's asking whether there could be an electric field in the universe.
So there could, you know, but first of all, you would need a mechanism to create such an electric field. I mean, for electric fields, there are everywhere, there are charges, okay, to begin with. A charge creates electric field. Now, if you are talking about a global electric field in the whole universe, say a homogeneous pointing in some direction, well, in order to have such a thing, you would need a mechanism to create that everywhere in space, which would be already pretty peculiar mechanism, but, well, physically, nothing prevents you from having it. Now, if there were such electric field, certainly its intensity is very, very small, because there is no detection whatsoever of any privileged direction in the universe of any kind. Certainly not gravitationally speaking, or not for motion of particles. Okay. So nothing prevents you from having it, but I don't think there is any observation that supports this idea.
Okay, should we move on now? Because
I'm definitely happy to move on.
Okay.
Shall I continue then?
Yeah, that's it. Let's continue.
All right. So welcome back, guys. Okay. Now we are going to approach the definition of gravitational waves. And we are going to see three approaches. This is why I'm categorizing this one as the first one. And they will go increasingly in difficulty. Okay, so don't be shy to tell me if at some moment you are not following, you are not understanding, because sometimes if you have not seen this ever, it's not so easy to follow, okay, given the difficulty of the theory itself. Right, so let me see if I can punch transparencies. First approach to gravitational waves consists in making an expansion of perturbations on top of Minkowski. All right, so we consider our space-time background is that of Minkowski, that of special relativity. But we still think of the gravitational field as being somehow dynamical because it has some perturbation, and its perturbation, because its absolute value is much smaller than 1, hence much smaller than any of the absolute values of the entry in the Minkowski metric. Okay. Now this is called linearized gravity. So in the textbooks. So when you see something referring to linearized gravity, it means linearize. It means the linearization of gravity, as we are doing, over Minkowski. Okay, not over arbitrary background, as we will see later. Now, if I'm making such an assumption that there is a space-time metric that can be decomposed into fixed background Minkowski plus perturbation, I am fixing the frame. I am choosing a set of systems of reference. Okay, that's what it means to fix the frame. So what happens with the symmetry invariance under diffeomorphism, general coordinate transformations, which was at the heart of general relativity? What's happening with this symmetry? Well, if I'm assuming this expansion I have there, we are losing this symmetry. This is not anymore a symmetry if I want to preserve this. Because if I want to preserve it under general transformations, I can make a transformation to boost so much my system of coordinates that I will certainly destroy this condition of having a perturbation over Minkowski. Okay. So the first thing we are learning is that if we want to do this first approach to gravitational waves, which amounts to assume Minkowski plus perturbations, this essentially amounts to change slightly the notion of what is the symmetry we are left with. Essentially, the general transformation of coordinates, diffeomorphisms, now becomes something residual, or there is a residual symmetry within the general diffeomorphism, which is something more reduced. It amounts for the following transformation. General coordinates, I can change them like this by addition of infinitesimal function to generate this transformation, under the condition that the space-time derivatives of this function are smaller than the perturbations themselves. Why is that? Because when you study how metric changes from one coordinate system to another, this is the transformation law at this linear level. It's just the same perturbation plus derivatives, the combination of derivatives, this is what this bracket means, of this generating function here. Okay? So you want this to be small as this, otherwise you will break this condition in first place. Easy to understand, I hope. Now, let us introduce this into the Einstein equation, the nonlinear Einstein equation, and we expand to first order in this metric perturbation. First, we do a trick that a priori you wouldn't know about it, but since other clever people have done this expansion for us, you recognize that when you do the expansion, it's very useful to define this so-called trace reverse metric perturbation, which is nothing else but the original perturbation here, minus 1/2 its trace times the background metric, Minkowski background metric. Okay, this is called trace reverse because the trace of this is the inverse of this one. Now you plug it in your Einstein equations. You build the trace reverse one in the resulting expression, and this is what it looks like: the Einstein tensor expanded to first order in perturbations, in general perturbations on top of Minkowski. This is the first order expansion of the Einstein tensor, okay? But now recall, don't forget that there is this residual symmetry. We said I can always change infinitesimally my location, my coordinate system, as long as this generator of the transformation of coordinates is such that its derivatives are small enough bounded from above by the metric perturbations themselves. If I can do that, then I can make a choice of what I want my coordinates, my perturbations to be. I can choose those frame of coordinates where I have the following condition, the Lorentz gauge. This is a choice. It's not every system of coordinates which respect the residual symmetry will have that, but I can choose the coordinates that will have that. Okay, how? It's a technical note. Imagine you're studying a location in a set of coordinates where you don't have this verified. Okay, no problem. I make a change of coordinates. I transform my metric perturbations into the new set of coordinates, and there is this rule, remember? And now I see that if originally here this is non-vanishing, well, the derivative of the new metric perturbation, I can always make it 0. Because I just have to take this one equal to this box operator over the generator of the transformation, and then that's it, you know? It's as simple as solving for what are these functions here, which remember generate the transformation, equal to this function, which is the original non-vanishing divergence. There are always solutions for this equation. Therefore, I can always impose, as soon as I found this solution, what is the system of coordinates where in such a system I fulfill this Lorentz gauge. Okay, very good. So let's assume we are in the Lorentz gauge in a system of coordinates. Why do I do that? Because if you had put attention to this equation here, you notice that you have contraction of the of the derivative indices with the indices of the perturbation themselves. So essentially, this is a trick to put to zero this just by a gauge transformation, a change of coordinates. And what I'm left with is a very simple equation now. I am left with a wave operator in relativistic description fashion over this trace reverse metric perturbation equal to this source of gravity, gravity. Okay? Are these gravitational waves yet? Well, let us first make the following thinking. We had a metric which is a symmetric matrix of 4 times 4 that has 16 entities, but because it's symmetric, only 10 degrees of freedom are independent in any metric, and any matrix symmetric 4 times 4. Now, thanks to the Lorentz gauge, we've consumed 4 degrees of freedom, okay? Because this is 4 choices, since there is 4 free indexes here. The mu can take 4 values. So essentially, now we are removing, or we are reducing the number of degrees of freedom from 10 to 6. Okay? But I'm pretty sure that even if you've never studied, maybe some of you have, of course, but even those who have not studied, you've heard that gravity has 2 degrees of freedom. So this cannot be all, okay? There's got to be something else, because otherwise I'm left apparently with 6 degrees of freedom. And this is easy to realize. Well, we said we are in the Lorentz gauge. That doesn't mean I cannot make further transformations. I can actually make, again, infinitesimal transformations because I had not saturated the gauge, because now I can find what are the new set of transformations that makes me move from one coordinate system to another, where I always respect the Lorentz gauge. And for that, I only need to solve box operator of this generator equal to 0. So essentially, this guarantees me that if originally I was in a Lorentz gauge system, then I move into a Lorentz gauge system. But again, these transformations are 4 degrees of freedom. So now imagine you are in a situation outside of the source, very far away from any source of gravity. Okay. Well, then exploiting the fact that I have another 4 equations here, I can reduce further my degrees of freedom. And I can choose these psi coordinates here, psi function, to choose, for instance, that the 0 component elements of the perturbation, the trace are 0, vanishing, and the divergence of the spatial components are 0. This is called the transverse traceless gauge. Traceless for obvious reason, the trace is 0, transverse because the derivative here linked with one index is 0. So it's pretty obvious name. And now we've reduced the number of degrees of freedom from 6 into 4. Sorry, from 6 into 2, because we removed 4 degrees of freedom from this further residual gauge invariant we had. Okay. Now, what happens if, however, we are not far away from a source and there is a source very close to us or even surrounding us? Okay. Can I take the transverse traceless gauge? Well, actually, you can't. You cannot, because the transverse traceless gauge assumes that the 0 component of your metric perturbations are 0, which will tell you through this equation that the 0 component, maybe 0i or 0, 0, of your energy momentum tensor is 0, which is not a physical requisite. I can surely have an energy momentum tensor with 0 index components. So what's going on? What's going on is that in this situation, there are still 2 degrees of freedom, but I cannot take the transverse traceless gauge. I just cannot make this choice. You may stay in whatever system of reference. Maybe you think you have 6 degrees of freedom. You can make a transformation of this kind to reduce to 2 degrees of freedom, but by this transformation, you cannot make the 0 component of your tensor vanishing, because this would not be allowed given the presence of your source. Yet, you still have 2 degrees of freedom. Okay. So in this first approach of gravitational waves, what we are discovering here is that if I'm out or far away enough from a source, then I can definitely take the transverse traceless gauge, which clearly characterize the metric perturbation by 2 degrees of freedom. If you think about it, Hij are the spatial components. This is a 3 times 3 matrix. Since it's symmetric, there are only 6 entities. Out of these 6, this equation represents 3 constraints and this one. So I'm left with 2 degrees of freedom. And this is the famous equation now of gravitational waves, okay, which is called like that because this is a wave equation. And this is why we talk in first place about these metric perturbations. We call them gravitational waves, okay? So very good question. Can they be gauged away? Can I make further gauge transformation and put them away or change how they look? No, because when we did the last transformation to remove the degrees of freedom to 2 degrees of freedom, there is no any residual further gauge transformation. We've saturated the gauge freedom, okay? So they cannot be gauged away. These are physical. Now, the problem we've learned, and we will correct this in the second approach of gravitational waves, is that, however, it's not guaranteed that I can take an easy gauge in the presence of sources where I can see manifestly these 2 degrees of freedom apparent immediately in the metric components. Okay. Let us think then of gravitational waves in this gauge, which is the transverse traceless gauge. Well, let us think of them of an entity of a space-time. Remember, this is a function that is defining how a space-time is fluctuating because it's on top of Minkowski, and it's propagating in the z direction, as an example, okay, without loss of generality. Now, they are called transverse because the transversality condition here tells you that this tensor can only live in the transverse plane of propagation. This is absolutely the same as with electromagnetic waves. Okay, absolutely the same. Let me move this from my screen, sorry. Yeah. Now, not only they are transverse, they are traceless. So this means that because there are 2 degrees of freedom, let us now expand our tensor field, living only in the transverse plane. So there are only indexes here running in 2 values, 1 and 2, say x and y direction. We decompose it in Fourier in this plane. And essentially, what you can learn is that there is only one possible way to write these transverse and traceless degrees of freedom, which is a matrix that in the transverse plane, that is this submatrix here, since it's traceless, this upper guy here has to be equal of opposite sign of this lower guy, and these off-diagonal guys have to be equal, okay? So this I will pass it to you as an exercise, and you will have to demonstrate that based on the fact that there are these conditions, traceless transversality and 0 components of the perturbation vanishing, then this is the only way to write the 3-dimensional Hij perturbation. So what are these symbols, plus and cross? They mean the polarizations of the gravitational waves. Gravitational wave, any gravitational wave has only 2 degrees of freedom, now we've said repeatedly, and these are sometimes called the plus and cross modes, because if you had a wave passing transverse through a ring of test masses, and the wave has active only the plus term, essentially the effect when it passes by, it's this one. It squeezes in the opposite transverse directions, and hence why this is called plus. Versus cross, which it will be the same squeezing, but just in the diagonal directions, okay? And I'm not gonna play them, but for you, I put some videos here. You have the links in the PDF where you can click and you will see this in motion, okay? If we have time at the very end of the presentation, we can try to click it, but otherwise you can play it yourself, okay? So gravitational waves have 2 polarizations, or degrees of freedom is the same, which are called the plus and cross. Okay, yes.
There are many questions. Maybe it's a good moment now before you enter into the second approach.
You tell me, I don't know what's the best. If there are many, maybe, how many?
Okay, let me pass you the ones which are still related to what you explained.
Okay.
So that people can follow them.
Exactly, because other general questions we can address them in Slack or, yeah.
Right. So one question by Nehal is, the transformations and the residual gauge still need to satisfy the boundary conditions, right?
What boundary conditions? Yeah.
Neal, if you want to elaborate more on your question.
Yeah. I mean, the point here is that if you want the only boundary condition I can think of is this guy vanishing in the infinite, you know, because here we are talking about transformation everywhere in space. It's just a small deformation of coordinates, but it's everywhere. So essentially, we need a function whose solution satisfies this wave equation everywhere in space and in time. Okay.
Okay.
And this is this residual gauge transformation, which in reality is the same transformation we did before in the technical box. Simply the difference is that now f is 0. So now I have box operator with Minkowski over the generator of my transformation equals 0. That's essentially that residual transformation, which are plane waves, by the way. So this is why I'm not sure what boundaries this person.
Okay, let's see if Neal can clarify his questions.
Yeah.
In the meantime, there's another question by Jenny. So she's asking, what is the meaning of the degrees of freedom in relativity? I think it was already partially answered, but maybe you want to comment. I mean,
so what's the meaning of the degrees of freedom in general relativity?
I guess he's referring to the propagating modes of the tensor you already discussed.
So somehow, just to answer Jenny interpreting her question, you see, when you write a general metric, because this is a symmetric guy, it has a priori 10 degrees of freedom, 10 functions. But they contain spurious degrees of freedom, which are not physical because they are not gauge invariant. And actually, you'll see now that when we make our second definition, we are going to look for a gauge invariant formulation of gravitational waves. Whereas here, there is no gauge invariance. There is no gauge invariant definition of degrees of freedom. What I'm exploiting is the gauge invariance freedom to choose specific frames of coordinates where these properties are fulfilled. So I see explicitly the fact that I'm left with only 2 degrees of freedom in those set of coordinates, okay? But in another set of coordinates, for instance, here, I could apparently think that I have 6 degrees of freedom. But this is spurious because I can still apply the residual symmetry, and even in the presence of the source, I can apply it. I may not be able to take the transverse waveless gauge, but I can certainly reduce the number of degrees of freedom from 6 to 2, just because there are the freedom here of 4 functions. Okay. So at the end of the day, what happens is, like in electromagnetism, you know, you have 2 degrees of freedom for your photon, for your gauge field, even though initially you write your Lorentz gauge field with 4 amplitudes, with 4 entries, 4 functions. But through gauge invariance, you realize that at the end there are only 2 independent degrees of freedom. That's the same here.
Nice. So Samantha Saha raised her hand. Please go ahead and ask your question.
Okay.
Hello, can you hear me?
Yes, I hear you. I hear you. Go ahead.
Yeah. Okay, thank you. So in the case of, as you mentioned, the transverse stressless gauge case, could you please go back to your earlier slide, previous slide, please?
This one?
Yeah. So in this case, outside the source, that H0 mu part is 0.
Yeah.
And here the degrees of freedom is just 2. And when the source, we are not outside the source, in that case, this H0 mu is not 0.
Correct.
But the degrees of freedom is 2. So
correct.
What's the extra piece of information this H0 mu adding?
So the point is, I see there is 6 functions which are related themselves, such that there are 4 constraints and only 2, and at the end there are only 2 degrees of freedom. But I cannot put to 0 explicitly 4 of those 6 functions. This is what I cannot do.
Okay, so
that's the idea. I cannot put them to, I cannot make them vanishing, because this would be in contradiction with the presence of the source. But that doesn't mean that they are not independent from, that they are independent from each other, the 6 degrees of freedom. They are still linked in such a way that through gauge transformations, I realize in reality there are only 2 independent ones, even though I'm writing 6.
Okay, I got it. Yeah, thank you.
In any case, be aware that now in the second definition, we are going to remove this problem. And you'll see this definition of linearized gravity, this is what comes in every textbook. For me, it's very confusing. Okay, it took me years to really understand, you know, why do I need to go to a gauge to define gravitational waves? And if I'm not in that gauge, then how do I make gravitational waves, etc. You will see in the second definition that these subtleties and confusion disappears. Okay, and I hope I will be able to address in a very different manner your question, actually.
Okay, another thing is how we can understand that all of those gauge fixing are already done. There are no residual gauge or anything.
Yeah, it's difficult. In the case of the transverse choiceless gauge, is because, you know, you are a priori, you are in the Lorentz gauge, okay?
Yeah.
So if you are in a Lorentz gauge, it means that whatever transformation you do, it should still preserve the Lorentz gauge, okay? Well, the only one you can do that still preserves the Lorentz gauge is this residual one. And this amounts for four functions, which are, if not arbitrary, certainly with a lot of freedom. And then you can reduce in 4 degrees of freedom further. So now, what kind of transformation could I do further to reduce the degrees of freedom? Nothing else. There is nothing else that I can do, you know. But is that satisfying? No, because I don't have a mathematical theorem, you know. Or if somebody does, I certainly not aware of it. So the way I prefer to do it is with this other second definition that I think is going to remove all these and all these subtleties. Okay. So I propose let's move on into this second approach, and I hope this will give you another perspective and why we shouldn't be so much worried about the gauge we are choosing.
Thank you so much.
My pleasure. Thank you for your questions. Okay, cool, guys. So I think I'm going to move on into the second definition of gravitational waves, second approach. This is what I call the gauge invariant approach. So now we are going to think again of a perturbative decomposition of our general metric into Minkowski plus some functions, general functions, which again we require to be very small. Okay, so we are breaking full general diffeomorphism, and we are only forced to move with infinitesimal diffeomorphisms. But this is fine. Okay, we are just going to make coordinate transformation from one infinitesimal frame to another, but without restricting what gauge choice we make. Why? Because now what I'm going to do instead is to decompose mathematically this tensor, which has 2 indexes, each of them running 4 values, 0, 1, 2, 3. Okay? I'm going to decompose them into the so-called scalar vector tensor decomposition. So obviously the 0, 0 part is a single function, so that's going to be a scalar. The 0i part, it can be a vector. So how we do it is we introduce a gradient of a scalar and a vector itself. And finally, the spatial part, that would be like looking like a tensor with 2 indexes. So we can introduce a scalar, another scalar from which we generate derivatives, or we contract with the metric, with the delta Kronecker. Then we could introduce a vector of which we take spatial derivatives. And finally, we could introduce a pure tensor. Okay? And the same decomposition can be done at the level of the source. The energy momentum tensor can be decomposed into a series of functions which are scalars, vectors, or even tensors. Okay? Let's be more concrete. So we put them now here very clearly in the screen, and this is the decomposition we've made. This is, let me call it SVT decomposition, okay? A scalar, vector, tensor. Here, a scalar, vector, and tensor are such objects with respect the rotations group. So since we are in Minkowski, this is homogeneous and isotropic. There is no privileged location or direction. So we are talking about how these guys behave as scalars, vectors, or tensors under rotations in this homogeneous isotropic spacetime that is Minkowski. Okay, scalars. Let's begin by identifying them. You see, in the metric decomposition, there is one here. There's another one here, out of which I take a gradient to generate one index here. There is another one here, which has to be contracted with delta ij, and another one here that can be used such that you do 2 derivatives, or you contract it with delta ij times a Laplacian. Scalars for energy momentum tensor, the same, just different letter, different notation. Vectors, well, here you have intrinsic vector, here you have derivative of vectors to generate two indexes. The same goes for the vectors in the decomposition of energy momentum tensor. And finally, tensors. So a guy that already has two indexes, spatial indexes. Okay, here the hij, here the pi ij. All right. A priori, I know that my matrix element or my energy momentum tensor has seemingly 16 degrees of freedom. But we know, because we've said it repeatedly, these are symmetric matrices, so there can only be at most, let's say, 10 degrees of freedom, because we know by symmetry, immediately we should remove 6 degrees of freedom. Okay, so somehow the way I've been counting scalars, vectors, and tensors was a bit misleading, because I didn't tell you that in reality, these vectors are subject to this constraint. The divergence of them is vanishing. So they are divergenceless vectors. Here this vector, here this vector, u1. Or here this vector, here this vector. Okay, I'm talking about the metric first here. The same goes for energy momentum tensor, okay? The vector u1 here or the vector vi here, they are subject to be divergenceless. So it means out of the 3 components, in reality, only 2 are independent. And this makes sense, no? Because now you can count degrees of freedom. If this guy has 3 entries, the scalar represents 1 degree of freedom, and this guy is divergenceless. So out of the 3 components, in reality, only 2 are independent. So 2 plus 1, 3 in total, representing the 3 entries I need here, and so on and so forth. And now the pure tensors, in reality, what it means to be pure tensor, it means that you are actually transverse and traceless. So these are 3 constraints for the transversality, 1 constraint for the traceless thing. So in totality, 4 constraints for the pure tensors. So in other words, all in total, over this metric perturbation decomposition of energy momentum tensor decomposition, there are 6 constraint equations in both of the systems. Therefore, immediately I see where it comes that my matrix is symmetric and it might have only 10 degrees of freedom, which we know are less, okay? But at least we need this reduction in first place. Okay, 10 degrees of freedom. Now, do we have more physical constraints? We do. We know that the energy momentum tensor is conserved. You should know this from special relativity, and there is the generalization of this in general relativity. And this means that the divergence of the energy momentum tensor is 0. So if you introduce this decomposition of your energy momentum tensor here, this amounts to relation between the different fluctuations, perturbations that were defining this energy momentum tensor. If I have 4 equations, 4 constraints, this means that out of the 10 degrees of freedom that I thought I had here, in reality, I'm going to have 4, okay? Which we were kind of 6, sorry. So, sorry, I'm saying this wrong all the time. 4 constraint equations, I subtract 4 to 10, so I'm left with 6. What about other physical constraints? Well, unfortunately, I don't have the equivalent same constraint as for the energy momentum tensor with respect to the metric. I rather have the equivalent constraint with the Einstein tensor, which is a bilinear, nonlinear construction of the metric tensor, a completely different issue. So we cannot do the same trick, but we can do something else. Let's assume we consider a general coordinate transformation, again, perturbative, okay, in the sense of this is a small function, and we transform the metric perturbation, as we know, and then we decompose this generator of the transformation into a scalar and a gradient of a scalar plus a pure vector, meaning is divergenceless. So the same fashion of the composition. This means now that if we take into account this transformation of coordinates, and this is how the metric element, the metric perturbation transforms, we plug it here with the derivative rule, and then we see how the different metric elements transform with respect to these elements that represent the generator of my transformation. And what we learn immediately, as expected, is that these seemingly 10 degrees of freedom are not gauge invariant. They change under a change of gauge, so under a change of coordinate transformation. Obviously, that's what it was expected. So we see that they change. They change in this fashion. But we also notice that the pure tensors don't change. They're actually gauge invariant by default, okay? And now this guy is 4 generators, if you want. So I remove again 4 degrees of freedom. I'm left with 6 degrees of freedom in total. Very good. So now I'm left with 6 degrees of freedom in both of each of these system of guys. And this implies, if I have this rule, this power to transform my metric perturbation, that there should exist some linear combination of them, maybe with potential derivatives, such that when I make a transformation, a infinitesimal general transformation, these are completely gauge invariant. And this is very easy to find. Well, not so easy, actually. You need to think a little bit, but you can find what are these linear combinations and define a scalar that is actually gauge invariant made from the other scalar with some derivatives. You can find a second scalar made from linear combination of the initial scalar with some spatial derivatives. And you can find a vector made again from linear combination of the two vectors you had in first place. Okay, we are talking, for instance, about these two vectors here and here, which again is divergenceless. However, when you change your general infinitesimal coordinate system, these guys don't change. Plus these 2 degrees of freedom of the transverse traceless degrees of freedom, well, now just count it. I have the 6 degrees of freedom I was expecting. 1, 1, 2, 2. Okay, 6 in total. So essentially, we can claim that because these degrees of freedom, we know they were 6 in first place, and we have already written 6 degrees of freedom that are gauge invariant, it cannot be reduced any further. Okay, it cannot. So essentially, we've written down that there are these 6 degrees of freedom that are gauge invariant and therefore won't change when I change my system of coordinates. Now, this implies necessarily mathematically that I should be able to write my Einstein tensor expanded as a function of these gauge invariant guys. So I've got to find a way in which, instead of writing in terms of the previous metric perturbation, which were not gauge invariant, now I could write it in the form of gauge invariant variables. Okay. So in other words, yes.
No, I just want to remember that you are now 5 minutes over time, right?
Oh, is that true? Okay, I see. Then
so
let me see.
It was until 15, right?
Yeah, okay. So thanks for letting me know. Okay, then I'm going to finish here, and the third derivation of gravitational waves, I will give it tomorrow. No worries.
Okay.
Yeah, thanks for letting. Or if you want, at 30 past, no, let's postpone it for tomorrow. Let's postpone it for tomorrow. Yeah. Okay, so let me just finish here. I'm about to finish in a couple of transparencies.
Okay, that's
so. Thanks for letting me know. So here, guys, realize what we have achieved. And you should really celebrate this achievement, particularly if you can derive it yourselves, okay? Which is really some long calculation, but this is incredible. We've managed to write in a gauge invariant fashion the Einstein equation at perturbative level, okay? And we realize that there are similarly 6 degrees of freedom, but we also see that these other degrees of freedom, the scalars and the vector, actually are only supported whenever there is energy density fluctuation, pressure density fluctuations, or velocity flows, okay? However, we do notice that our pure tensors actually are very special and different than the other equations, because the other equations satisfy Laplace equations, whereas our pure tensors satisfy a wave equation. So what we have discovered here is that when I decompose over Minkowski, which is a homogeneous anisotropic space-time of metric fluctuations, the transverse traceless degrees of freedom of my decomposition, which are gauge invariant because they won't change from one coordinate transformation to another, are actually the only ones satisfying a wave equation. So this is another perspective to say that the only identification I should make with gravitational waves are precisely the transverse traceless degrees of freedom of my metric, because these are the only ones propagating. Only radiative degrees of freedom, radiative means that they propagate through a wave equation, are gauge invariant and actually propagate, okay? So only these tensors, if you want, are the radiative degrees of freedom, which furthermore are gauge invariant, okay? So gravitational waves are to be identified with the transverse traceless part of your metric perturbation, independently of the gauge, because transverse traceless degrees of freedom are just a part of your metric perturbation. What we achieved before in the first definition is we realized that we could find certain gauges, certain system of references, where we could make manifest that all our perturbations were vanishing except the transverse traceless degrees of freedom. But I don't require that to define gravitational waves. What I require is to decompose into a scalar vector and tensors, and it is the tensors precisely that represents the gravitational waves. Okay. So given that I'm over time, we are gonna cut it here. Maybe I'm happy to take questions, of course, if you want, for a few minutes, because actually at 5:30 I have another meeting. But let's cut it here, and we continue with third definition tomorrow.
Great, thanks a lot.
My pleasure.
Daniel. I think it was a great lecture, which you can see from the amount of questions.
Great, good to know. Yeah.
So, okay, I'll pass you a couple of questions, and we will leave the rest for Q&A and Slack. You just open a Slack channel for gravitational waves Figueroa, where you can address to him all your remaining questions. Okay.
Yeah.
So, okay, one question from Ganesh is the scalar vector tensor decomposition the same as ADM decomposition?
No, that's a different decomposition. That's a completely different decomposition. That has to do with how to separate the flow in time compared to the flow in space, if you want. So ADM decomposition is, if you want, a more general decomposition of a metric, which is also was fundamental discovery, if you want, or fundamental proposal in the early 60s, in order to really quantify what are the degrees of freedom in gravity, which are 2. So in order to figure out that there are 2 only degrees of freedom propagating in gravity, one doesn't even need to do this scalar vector tensor thing. You can do with ADM decomposition, which is something else, slightly more complicated. However, I think whenever your space-time is homogeneous and isotropic, which is certainly the case of Minkowski physics or of the whole universe through the Friedmann-Lemaitre-Robertson-Walker metric, then this is the best way to see in a transparent and clean way what are the part of the metric perturbations to be identified with gravitational waves, and therefore the propagating degrees of freedom of gravity.
Good. Then there's a question from Noel. He's saying, if you have the Einstein equation with an energy momentum tensor which has a vanishing 0 mu component, for instance, for tensor modes acting as a source, could you still have h mu 0 equals 0?
Yes, in principle, yes. Yeah, in principle, yes. I mean, not that I have a mathematical demonstration in my mind, but a priori, the impediment precisely to make the h0 mu equal 0 was the fact that typically t0 mu is non-zero. So now the question is, can you really have the question, I will bounce it back to this person. Do you think we can have an energy momentum tensor with vanishing element with 1 0 in the index? And I anticipate you, this will be extremely weird case. Why? Because the energy density of a system is identified with the 0, 0 component of the energy momentum tensor. And the momentum and part of the angular momentum also carried by any system is also identified with the 0I components. So the question is, would it be possible to write a source that don't have that vanishing? I'm not sure. I would rather say it would be very bizarre source in case that is even possible.
Okay, I think we should close it here. So thanks again, Daniel, for a very clear lecture and beautiful slides. So
my pleasure. Thank you.
We'll see you again tomorrow. And now I want to recall to everyone that the schedule of today is wrong because we are meeting